Okay. So, but it does not mean that we can't learn it. That also we need to understand. So we have to manage it. The only thing we have to do is that hard work and commitment. If you have all that, then surely we can achieve anything in the life. So just to get some idea, I'm asking all of you to go through the story for 2 minutes. So the moral of the story is that there are two people, Tom and Chris. Okay, you see here, the difference is that one person came only to get just to do the job, whereas the other person, he involved and he learned each and every component or how that entire okay, railway track or railway mechanism works. So because of that, he is able to start his own company. But other person, okay, is able to do something, but what is that? Only is able to complete his job properly. The same way, here, if the people who are attending only for the sake of certificate, you will get certificate. Surely you will get certificate. But one thing I'm telling you, you will get only certificate. You won't get anything
Technical
other
way.
than. Okay. But whereas the other person who is
ఇది
really
పెట్టవే ఫోన్లో ఇప్పుడు అడ్రస్ ఉంటుంది నీకు నువ్వు వాట్సాప్
yeah, the other thing, the other category is that the person who are here to really learn something and do something related to this, then accordingly you will get the benefit. So I don't know. So how many of you are really only for certificate? So I think it is of waste of time to you. Okay, because what is the use? You will get these days. You will get hundreds of certificates if you register somewhere. It doesn't matter. Okay, so please concentrate on it and make sure that you are getting something from this session, or not only from this session, any other session that you are attending. So, but from there we need to explore it. So that is what everybody is doing, and even we also did like that, and even others who are really achieving something in the life means they are contributing in that way. So if you want to really achieve anything, whatever you expect to achieve in the life, you should have that ambition to receive it, achieve it, and hard work. I always believe in this hard work. Another one is commitment. Okay. Then why generally in most of the sessions I generally give this one two slides here just to make sure that what is the purpose of attending this. It is only for time pass means okay. It is like that only you will get if you really feel that you want to learn something, but you can achieve it because one no, as the technology is new. So the people who learn this new technology in the beginning era of that, so they'll be getting more benefits that we know. That is no, that is the fact which has started from at least to our generation. We can say that those who learned computers, they are no getting good jobs. And whether you believe it or not, around in 2000 year, actually there was a lot of boom about that IBM, um, not supercomputer, some IBM frames, I think. So during those days, so those who learned just how to start and stop the IBM computer, people just for love, no, love for sense, they used to say that they went to USA because during those days, just operating with that IBM mainframes itself was a great difficulty. So those who learned just how to switch on, switch off the IBM computer, they know USA has taken those people, and because of that, they good succeeded in their life and getting good salary and everything. In the same way, as people are talking about quantum computing, at least to our generation and to our level, everybody feels like it is new technology. So my advice, sincere advice to all of you is that take the advantage of the timing. If you start learning that quantum computing and quantum technology now, it is useful to like no do whoever is learning it now. But if you say that you want to learn this quantum computing after 20 years, so it is same as like learning IBM frames now. It is of no use now. In 2000, 2001 year, then there were very less people who were doing something on that. So because of that, they got good job and settled in their life. So please you keep that in mind and start attending all the sessions related to this quantum computing. Surely we will achieve whatever that we want to achieve in this. Okay, right. So here, as my basic research is in image processing, from past 25 years, I am in image processing only. But as and when some new technology comes, like previously I used to work with big data, with image processing. Okay, after a few days, as the people know, I started using deep learning and image processing. I explored that. Now I'm exploring how to use this quantum computing environment for image processing. But to surprise to the no, to my surprise, I saw in the internet one article or almost like no reference summer. I found this paper. So that means after seeing it, then I realized okay, that means people are doing quantum image processing from past 20 years. Okay, but now at least something is better than nothing. At least today we came to know that we also can do something in that. Then you may be thinking what we can do in the same quantum image processing after 20 years. So I don't believe in somebody saying that okay, this field is saturated or that field is saturated. You need to create it and you need to continue that field. That is the good thing in computer science. Okay. Now to work with this quantum image processing, so you need to know obviously about quantum computing and about image processing. This is the fundamental diagram, and those who knows about image processing, I think surely you might have known this top part with blue color. That is the computer that is used or so far is known as classical computer. And whatever the process that we have done, that is by using only zeros and ones, that are known as bits, and doing after doing something to those numbers, we'll get the resultant ones and zeros. After displaying, we are getting it. So that means ultimately, what I mean to say that so far, whatever the image processing that we have done, this is on classical computer. But now I want to do image processing only, but the computing environment is different. Now, please, all of you tell me, if the environment changes, do you think that answer will change? Or technology changed, answer will change or not? I think all of you have decided not to respond. Okay, at least is my voice audible?
Yes, sir, you are audible. Yes, sir. If environment changes, the answer will also change.
Okay, right. How? Okay, you tell me the answer for this. Let us assume that you are using a abacus. So, if somebody asks you to tell me the sum of 2 plus 3, what is the answer? 5. Let us assume that you are using a calculator and question is same. What is the answer? 5. And you said that you have written a program to add two numbers, but question the input is 2, 3. What is the output? 5. Here we have used computer. Okay. Now I'm telling that so far we are using classical computer. So 2 plus 3 is 5. But now I'm using another computing device. Okay, the word whatever that I precede before that, it doesn't matter. Then what should be the answer for 2 plus 3? 5 only, no? Okay, I think maybe I might have asked the question in different way. I should have asked it like that. But maybe our friend who told this answer, he may be thinking about environmental factors and so on like that. But I should have told this example beginning itself. At least for this one, is there any change in the answer? Abacus
Like,
is,
like there is no change in answer, sir. That's mathematics.
yes,
But coming to coding point of view, we may have different ways. Like finally, the answer will be same.
yeah, it must be same.
Yes.
Answer must be same. So now, previously, so we are telling that so far we are using classical computer, and we are able to say that 2 plus 3 is 5, where our elders, those who have used abacus and who have used calculator, or before this, any other, do you know any other device which can be used to do addition of the two numbers other than abacus? Okay, at least something known as Napier bone. Have you heard? But of course, our generation, none of us might have seen it. But if you go through the internet, you will be seeing the diagram of this. So this is also one of the calculating device. So surely those days, those who have used this device, if they want to find sum of 2 plus 3, they also use it to say 5. So whatever the device that you use, ultimately the answer is not changing. At least for this mathematical answer is not changing. Now, instead of classical computer, now I am telling that we are going to use quantum computer. But first of all, you need to consider this quantum computer is also nothing but one computer. Okay, so answer must be 5 only. If somebody is saying that they have some new technology, so there I'm getting 2 plus 3 as 5.00001. And you go and tell it to your grandfather, saying that okay, during your days you were telling 2 plus 3 is 5, but now recently we found new technology where we are getting 2 plus 3 is 5.001. Then they will laugh at us. Okay, so what should be the answer? We must say it is 5. Then they will think that okay, after spending so much of money to my grandson, at least he's able to tell the correct answer, not telling some wrong answer. And he is telling he learned quantum computing. From then onwards, he is telling 2 plus 3 is 5.00001. If you tell like that, that is blunder. Okay, so ultimately, one thing you need to keep in your mind is that by using quantum computer, we are not doing anything great what our elders have done. What we are doing here, we are doing the same thing what our elders have done, but doing with some new technology. But people say it is bit even faster. But you can't say that because I am doing faster, that's why 2 plus 3 you consider it as 5.001. Then if you say like that, people will say, no, you need not do any calculations. Okay. So please keep that in mind. Because people may be tempting because the new technology I learned, so I'm getting this answer. So nobody should ask me the question why 2 plus 3 is 5.001. If you start telling like that, it is of no use. Okay. So now, so far we use a classical computer to do some image processing. I'll tell you what is image processing, some processing. Now, when you want to work with quantum computer, as I told, the answer has to be same, but the technology that we are using is different. That means first you need to convert the classical representation of the photo into quantum representation. And I think so far you might have gone through some lectures organized by our JNT UK, and in that you might have come across something known as a bit and quantum bit. Is it right? What is a qubit? What is the difference between these two? It is also bit, but as it is used by quantum computer, generally they are calling it as quantum bit. Then how it is different?
Superposition.
Yeah, very good. So can you tell what is superposition? Yes, possible. Can you elaborate? 1-2 lines, that's all.
Both states at the same time.
Yeah, very
Zero
good.
and
Yes. So that means whatever that you are operating, that is assume that as it is there at multiple stages. Okay, when you say that you are operating on that, that means you are operating on all at the same time. But initially, I also struggled a lot to understand how we can say that something is existing at all the locations at the same time. But that is the beauty, or that is the thing that at least you need to convince yourself, say that okay, there is something known as superposition concept. Okay, so once if you understand that superposition, I think you can enjoy the whole quantum computing. Right, and here Bit means it is only at either 0 or 1. So here people used to say it can be 0, 1 or any other possible states of 0, 1 combination. It is it can be existing at multiple states at the same time. Okay. Anyhow, so then now as in the classical we use bits. In quantum representation, I need to represent the same image which is given to us in by using some quantum bits. So there are different representations of that image. I'll show you in the coming slides. But once the data is represented with qubits, obviously we can't use classical computer to process it, because classical computer can process if you are talking in terms of 0 or 1. But whereas here, you can talk by using the concept of superposition. Yes, now you give that superposition state of your quantum system to the quantum computer. Then obviously, once again, you will be getting the result in superposition state. Then at the end, to see the final result, you must convert back that quantum represented data into bit representation. That is known as a measurement. I think all of you might have come across the word measurement as when they discussed about quantum circuits. Obviously, that is one no concept. Finally, you need to measure. Measurement is nothing but converting quantum representation back to classical. As of now, to see the final result, we must convert it back into classical representation. I think all of you are familiar with this terminology. Okay, if not now, I think by chance, if anybody is not familiar, if just as you are coming across this terminology, better you remember that you heard these words. After that, you need to explore them. Okay, right. Now this is the whole quantum image processing. Once again, I'll tell you what is the meaning of this. So once the given is image is given, you need to convert that classical photograph into quantum representation. Give that quantum represented image to the quantum computer. You will get the result once again in qubit, and finally you need to convert that back into classical representation. Then this entire thing is about the whole image processing. Because I know I am in this image processing from past 25 years almost, I can say. Okay. Ultimately, then if you want to know about what is image processing, what to talk about it, then people who are talking about the image processing, then they need to do it on quantum environment. Then we'll say that they are also capable of doing some image processing on quantum computer. Now that same diagram is I have taken it from this resource, but the meaning of this diagram and previous diagram, they are exactly same. This is the original image, converted that into quantum representation of the data, then given to quantum computer. Result is in quantum representation. Final result in classical. Okay, right. So this is known as quantum image processing. Okay, then what is image processing? I think all of you are a little bit comfortable with this quantum and quantum terminology, no? Okay, otherwise, if it is required to do when I discuss about quantum algorithms, there I will surely give some something related to even to this quantum terminology. Just let me complete this image processing part. So here, what is this? This is considered as human vision. So what we are seeing here in this photograph, there is a person who is observing this photograph by his eyes. Then whatever that he captured with his eyes is sent to the brain. Actually, brain is the processing unit. Then whatever that he captured with his brain is sent to the captured with his eyes, sent to the brain, and whatever the knowledge that he is having in the brain, based on that, he is able to tell all these words related to this photograph. And now let us assume that he is around 25 years person. Now, instead of this 25 years person, let us assume that I keep on 3 years kid, and assume that this 3 years kid eyes are even bigger than this 25 years person. Do you think that he also can tell all these words about this photograph?
No, no, sir.
No. No. Why? Can I know the reason?
Because like he don't have any previous knowledge.
Yeah, because he don't have the knowledge that a 25 years person is having. Okay, so that is truth. Very good. Thank you. Now, the same thing. Now I am talking about computer vision. Previously, I talked about human vision. Now I'm telling computer vision. Now, in place of that sensing, that is I kept this camera. Do you think that camera will tell all these answers? Do you think previously just by seeing can he tell the answer? No, because whatever he has seen, it is sent to the brain. Because of that, he is telling the answers. In the same way, here, if I keep the camera, if you ask the camera to tell what is there, it won't tell. Then you need to connect that camera to the computer. Let us assume that in this computer, you have written 3 programs. And one program is how to know the color or how to distinguish color. Then how to know whether tree is there or not. And one more program to check whether bridge is there or not. Okay, now I have given that same photograph and as input to all the 3 programs. Then first program, what is the output of the first program?
Like a
Color.
RGB image.
Yeah, it will say green. At least mostly it is green in color. It will say green color. Tree is there or not? So what is the answer? Yes. Then bridge is there or not? It will give yes. Now instead of this, now you are asking one more. Actually, you have only 3 programs. But now you have given this photo as input to this first program or any of the three programs, and you are asking what is the name of the flower. Flower in the photograph. You asked the first program. What is the answer it is going to tell? It will say, I don't know. Second, it's okay, you went to second program and you asked what is the name of the flower. Because here, what is the code that you have here? Just to check whether tree is there or not. Then when you ask this question, obviously that is also will also say that no, I don't know like a flower about anything about flowers. Then if you ask the third one, it will say no, I also don't know anything about flower. I know only whether bridge is there or not. Okay, exactly say the same thing that has done previously. So when you say 3 years kid, he knows the knowledge only about these 3, and his brain is updated with that much knowledge at the age of 3. Now, how we can say that 25 years person is telling the answer to this question, what is the name of the flower? Because after this, in the same computer, I have written one more program, the names of the flowers, how to know the names of the flowers, then how to count the number of flowers, how to check water is there or not. So like that, I have written another 22 programs. So altogether now 25 programs are there in my computer. And here also I'm telling 25 years person and 3 years boy. And here also I'm comparing a computer with 3 programs and 25 programs. So in the same way, okay, as you want to get the information about all the 25, your computer should be updated with all 25 programs. Is it right or not? Okay. Right.
Yes, sir.
Yeah.
Yes.
Now our task in the whole computer vision is to replace this. That means what? Whatever that you were asking previously, the 25 years person, we need to ask now this computer. How you can ask this computer? If you write the programs for all the 25 questions that anybody is supposed to ask. Then, but how to get that photograph? In addition to this, you need to attach one camera and you focus on some location where you want to get the answer to all the questions, then capture the photo and give it to this. Then it is going to tell all the answers. Now same, if for example, even this brain is also having the answer for all these 25 questions, then will there be any change in the answer given by this human or this by computer? Same 25 things are updated in his brain. Let us assume at the age of 25, he is able to do all the things, whatever that we have written as a program. Then who is going to tell the correct answer? Both are exactly same. Because no, here I'm telling I told it to computer, but here I'm telling it to that I told the whole process to one person. Then we know that whether whether I told it to you or somebody else, if everybody is following my instructions, irrespective of the person who is using it, it has to be same. Let us assume that school days, so your teacher taught how to add 2 plus 3, and the same thing taught to your friend also. Then after that, if anybody asks who is doing the correct calculation, then what is the answer? If both of them are understood perfectly, because it is same thing, no? The teacher is explaining to everyone, and if you assume that everybody understand it exactly the way in which the teacher told, then there won't be any difference among the these students. We can go to any student. If you ask 5 plus 5, they can tell the answer because everybody follows the same steps what the teacher told. What the teacher might have told at that time, take 5 fingers from left hand and 5 fingers from right hand and count after 5 after 6, 7, 8, 9, 10. In the same way, then as I told the same thing to both, they are going to give exactly the same thing. Now in our entire computer vision, our target is to replace this. Means what? Whatever that a human being was doing previously, so my camera attached with computer has to do the same thing. Now you may be thinking what is computer vision, then what is image processing, what is video processing, then what is machine vision. So please don't waste your time in finding out the differences among all those subjects. Frankly speaking, I'm in this image processing almost from past 25 years. Even I too don't know the clear-cut distinction between all these 4 subjects. But only one thing I can tell is that everything, whatever we discuss, is nothing but seeing and doing. Okay, now previously seeing is with eye and doing with brain. Now I'm telling that no. So I'm not getting the people to do this for me. So then I replace eye with camera, then brain with computer. If I have money, I can have so many such systems in my lab or in my house or wherever I want. So this is the whole computer vision or image processing or video vision, video processing or machine vision. Don't waste your time, as I told you, no, seeing the gap difference among all those. Even if somebody asks me what I'm teaching now, I'll always say I'm teaching this part of this Venn diagram. So what is this one? Which subject out of these 3? The one which I am highlighting.
The combination of computer vision, machine vision, and image processing.
Yeah. So if somebody else will say, I know only this part. But of course, I'm comfortably managing my life for past 23, 20 years, 20 in image processing. And surely with the same knowledge, I can complete another 10, 15 years in my academic career. Okay, so please, whichever if you want to just somebody ask, even if you go through any textbook, you won't find. Some textbooks say something, some textbooks will give some other thing. But even that's why now I've given one more diagram. Actually, this is the diagram I've taken from Stanford University. And this is the view of another professor who is working there. He's telling computer vision and machine image processing very overlapping is only this much. If somebody asks, I'll say that I draw another diagram, something like this. I'll say just a little bit outside, I'll say this entire thing is okay, only this extra part I say I don't know, but this entire thing, whichever is covering everything, other than that, the line which I have drawn outside is something else. Other thing, everything is image processing. Okay, so if somebody asks, I can convince what is it. It is all about, and please you see here, the things which people are doing, no, seeing and doing. Okay, need to be replaced with, okay, camera and processing unit. Now you tell me what could be the projects that you can consider which can comes under image processing projects. You need not ask anyone to tell the project name. So you go through, if you go through the nature and if you feel that you are not able to process something by seeing every day. Okay, let us assume that my task is to count the number of students coming through our gate. That is the Humanity Warangal gate. my task is that, and then somebody asked me to sit there. Okay, so my duty is 8 hours, let us assume. Then assume that I am a little bit expert in image processing. Then obviously what I am going to do? Okay, instead of me sitting, I'll keep one camera and attach it with computer and write all the programs, whichever I know and whichever is used to count the number of people, how to recognize the people, how to count them, and I'll go to some other place and enjoy my life. Then I'll say that yes, I want to do this project only because I need it. Nobody should ask me why you have done this project, because see how the projects generally come and why that software people are doing that projects, why people really started working on railway reservation or banking, like what is that, computerized banking. Do you think that before computerized banking there was no banking system in India or in the entire world? Is there or not? People have, even my father and grandfather, they also used to go to bank and they also needed to deposit the money whenever they have that and they want to money. They used to go to bank and they withdraw the money. And during those days, when they went to bank and say they deposited 5,000 rupees, after a few days, if they go to bank, if they ask the people how much money is there in their account, they used to say that 5,000 rupees. Okay, no computerized bank, nothing. Now these days, let us assume that you deposited 5,000 rupees in your account by something known as so-called computerized banking. Let us assume that you deposit the money today. Okay, let us assume that you go and you have not done any transaction after that, and you went to bank on 30th of this month. If you ask what is the total amount in your balance, so I think it is going to be 5,000 or 5,500.
5,000 only.
5,000 only. Then what do you have done extra? During those days, our grandfather's days also, when they deposited 5,000, there was 5,000. Even now also, it is 5,000, 5,000 only, no? So,
Yes, sir.
yeah, that means, okay, they are enjoying banking and they were able to do everything. But, as the technology came, then people thought that, okay, just to going and depositing and doing all these things, it is taking a lot of time. Okay, of course, if you believe it or not, in our childhood, if my father need to go to bank, means it's almost like one day work to him because there is no bank in our village. So he has to go all the way from our village to another village, around 3 kilometers. Okay, then he has to deposit and he may need to wait there for 2 hours, 3 hours if the people are so many there. But finally, he's able to deposit and come. But now also we are doing the deposit means deposit, withdrawal means withdrawal only. But at that time, people might have observed it is taking a lot of time. Okay, let us assume that some company TCS thought that okay, as it is taking a lot of time, we will build one software for it. So in that software will be doing instead of the human being is doing. That's all, no. So here also 5,000. And if you go to deposit machine, nobody will be there, no human being. There will be one machine. So that machine also will be having computer like no vision part. Can you tell me what is the vision part in that money depositing machine? Can you tell me? It means computer is seeing. That means whatever the notes that you keep inside the depositing machine, surely there is going to be some vision system. It is first it will see the note and process it. Have you ever experienced it? If you go to any money depositing machine, by chance if you deposit any note with ink, or if you deposit any ink or anything with oil, it won't take. Have you experienced it? Yeah, I experienced
sir.
it. Yeah. So we experienced it. So that means what? There is some camera which is seeing your note and processing it. So processing means whatever that it is captured, it is given to the system. Just observe it, whether there are any what is that? oil marks or ink marks or anything, then simply it will discard it and it won't allow inside, and it will send it out to us. Okay, so that means in the whole, so that's why that is one of the project which comes under part of computer vision. I'm not telling that the whole depositing machine is based on computer vision, but computer vision is also part of it. And now people are talking about surveillance cameras. Why we need to have surveillance camera? People, like, previously also people used to exist, and the entire world was, so good without surveillance camera also. But why we need to have surveillance cameras? Okay, people, they want to observe something continuously. Obviously, they need to hire one person who is observing it continuously. So as we can't hire the people, so in place of that, we keep one camera, and it is keep on like observing, and whatever it observed, it is going to be kept in one computer. If you want, you can process it. So like that. So don't think about somebody gives you the problem to work with image processing. But of course, it's impossible. Maybe it's very difficult to find out the problem by ourselves in the beginning. Those who taught image processing, or those who are in image processing for so many years, they can explore and they can get it by themselves. Otherwise, you see, these are all the different applications. In all these things, whatever I have given, there is something considered as seeing and doing. Okay. But now, if you see one medical image processing, that itself is one vast domain. People are using no image processing technology, like technique, to work with in the medical domain, then remote sensing, then entertainment and media. I think we are getting to know all these movies with different animations, different VFX, or some effects and everything. All those comes under image processing part only. Okay, right. Now, once again, we'll go back to quantum computing. So far, frankly speaking, I haven't told anything. Just I told what is quantum computing and what is image processing. This is nothing but seeing and doing need to be replaced with seeing and doing only. But now, who has done previously? Seeing and doing is done by human being. Now, seeing and doing need to be done by one computer with camera. So then, what is quantum computer? That means we have seen the difference between classical, at least terminology, classical and quantum. But one thing you need to remember is that both are computers. And this whole quantum computing is made with the technology that is quantum physics, and okay, and there we use quantum bits to represent. So this is the actual content, that quantum bits, how they can be represented, what are the different algorithms, what is that quantum circuit. So that is the actual content for our computer science. Okay, as in the beginning I told, if you explain about something about quantum computing, so if you ask a physics professor, he will talk more about the superposition, entanglement, then interference, and all that terminology. But frankly speaking, no. Okay, once if you understand little bit about superposition, you keep that in mind, and directly you can jump into our computer science part of quantum computing. And one more thing I am telling you, nobody knows everything, that you keep in mind. But it does not mean that we can't do something. I think there are some good proverbs in English. You can say it, everybody can do something. So generally, I believe in that. And based on that, we started exploring it. Yeah. What is the quantum computing that you learned so far? Have you come across this statement? So what is the meaning of this slide? Anyone, I think? Have you heard about this Willow chip?
No, sir.
Okay. Well, then just after this, surely I'll go to the technical part of quantum computing. See, actually, this is the chip given by Google around 6 months or 8 months back. Quantum chip. You can almost consider it as quantum computer. So according to their claim, they are telling that if you give, I think before quantum computer, there was something like, as of now, all of us know that there are supercomputers in the world, and they are the best, the fastest computing environment that we have in the world. Of course, India may be having one supercomputer, but some other country, US or China, may be having another fast supercomputer. Maybe after 1 month, we may get another supercomputer. But they are the computer devices which can do the things very fast. Okay. Now, like 6 months back, this Google has given one quantum computing chip. The name of that is Willow chip. According to their claim, they are telling that if you give a task, some computing task, to the best supercomputer in the world, and if you assume that it is taking 10 to the power of 25 years to complete that task, which computer is doing that? The best supercomputer in the world. And it is assumed that it will take 10 to the power of 25 years. Now, if you give the same task to their Willow chip, that can be completed in 5 minutes. So that is what their claim. Is it believable? How many? Okay. The task which is going to be done by the best supercomputer in the world, if it takes 10 to the power of 25 years, I'm telling not days also, that task can be completed in 5 minutes. Because when I saw this statement, I also haven't believed it. Initially, I thought that what is this? Then I have gone through the internet and gone through different sources. And this screenshot I have taken from some of the YouTube is given by those people only. It is clearly shown here, 10 to the power of 25 years and 5 minutes. Really, if you want to feel the power of the actual quantum computer, so you must always remember this statement. Never, never, never forget it. 10 to the power of 25 years equal to 5 minutes. Now let us assume that after a few years, somebody has given another quantum computer which may take half of the time. So that means they are telling 2.2 minutes. What is half of 10 to the power of 25 years? Anyone, please, can you tell the answer?
2.5 minutes.
Yeah, minutes it's okay. Now 10 years here, 10 to the power of 25 years. What is half of 10 to the power of 25 years?
10 power 13 years.
No, okay, good. Now, okay, let us, what is the half of 1000? We'll go like this.
500.
500, no, good. So, 500. Now, instead of this, I asked you a question, same question, 10 cube. You told the same answer. What is half of 10 cube?
It is
10 power
500 into
24.
10 power 24.
Yeah. Now you tell me, by using this example, you tell me, now what is half of 10 to the power of 25? Yeah, one of our friend is telling, what is that? 5 into?
500 into 10 power
10 power
24.
24.
Yeah, 5
5 into
10
10 power 24.
Yeah, 5 into 10 to the power 24. Now, even this is also a very big number. No, if somebody said that they made another chip which is half of the previous time, then you imagine 5 into 10 to the power of 25 years. Then, because now I'm giving this example everywhere because you need to feel that number. 10 to the power of, even if somebody say 5 minutes to 2.5 minutes, it looks like very simple. But half of 225, 10 to the power of 25, which is nothing but 5 into 10 to the power of 24. That also is not a small number. Okay, so you anytime if you want to really feel or experience the power of quantum computing, every time you remember this. Even I think in future, instead of 10 to the power 25, they may go even more than that. But this itself looks like unbelievable. Even I'm not getting what kind of task is there to really to say that it is going to be done by the supercomputer, which is going to take 10 to the power 25 years. Okay, I think that's why generally people are telling no. I think all of you have studied the RSA algorithm. Those who are from computer science. RSA algorithm. Have you heard about it? In security. Or during our days, we studied this algorithm in computer networks, which is at that time we used to have one algorithm which is covering some part of security. Not RSA, I'm not sure. Okay, anyhow, have you heard about RSA algorithm or not? Actually, this is used in our banking because it is used mainly to find the prime factors of a given number. Okay, actually, once the number is little bit bigger, I'll tell you what is that bigness. It is almost impossible with the existing supercomputer to find the prime factors of a given number. Now let us assume that I have given 15. Can you tell me what are the prime factors of 15? With only two numbers. That means n is given, you need to tell n1 and n2. Where n1 and n2 both must be odd prime numbers.
3 and 5.
Because, yeah, 3 and 5. Okay, it looks very easy, no? Then 21, 3 and 7. It is satisfying, no? N1 is odd, N2 is odd, and both are prime. And only with two numbers we need to tell. If I tell 8, what are the prime factors of 8? 2 into 2 into 2.
It is not possible.
Yeah, because no, we are telling you need to use only two numbers, N1 and N2. But here we are using three numbers. Even I said it has to be odd, but you are using odd. So that's why be cautious about saying prime factorization. Actually, most of the books, they simply tell prime factorization on a given number. But if you go inside, they'll be adding these rules also. As the number is very small here, you are able to tell it. If you give a 20-digit number, which is having N1 and N2, actually it is having it. But to get these values for this 20-digit or 40-digit number is no, almost even after 100, 200 years also you can't get it. You can't able to find that. Then people may be thinking what is there, because I'm able to tell for 15, 21. So you go through the books and you will feel why you can't tell it. Okay, so now that is the status, and that particular part is used in RSA algorithm. That's the whole RSA algorithm. It will give n and asking no. Then believe that people can't compute n1 and n2. That's why the our banking system is running as of now. But when you go with the quantum computing, here we have one of the algorithm that is known as Shor's algorithm. I think I'll show you the names in the coming slides. This Shor algorithm can be actually he has given some mechanism to use or to get the factors of this given number. Okay, in quantum computing environment. So according to that, he is proved that you can compute the prime factors of a given number, which we felt previously take 100 years or 200 years. It can be done in 2 minutes or 3 minutes, something. But usually we can do it. So that is the power, because as some of our friend told, superposition, you keep that the word superposition and make sure that you are convinced with the concept of superposition. Then only you can feel the subject. Okay, right. Then this is, I think, story, the background of this entire quantum computing. I'm describing. I think you know what is superposition and entanglement. Okay, but as we are from computer science, I'm skipping the terminology, assuming that you already come across that. But at least you must know what is bit and qubit. So that is what I think some of our friend told in the beginning itself. And generally that qubit can be represented by using this. Yeah, and one more thing I want to tell is that as I taught this subject in our college, and really if somebody want to learn this as a course, my suggestion is better you go through either NPTEL or Coursera or any other online resource and register for the course and make sure that you are writing the exam, so that we can say that you followed some predefined syllabus and you are comfortable or with this, at least this whole syllabus there. Just initially, as I told you last summer, directly I started with quantum image processing. Okay, little bit I explored, but the technology that I heard during those days, so they applied and I tried my level best to take the course. This semester. So that's why I'm telling it. So you must do something initially if you are okay, but after that you must do some course. Then you will be perfect with the technology. And after teaching that course, what I understood is that to really know theoretically, you need to know only two things in mathematics. One is about your complex numbers. This is school maths only. And the other one is vectors. Without going through these two topics, revising these topics, if you try to attempt understanding quantum computing, that algorithms, it is of no use. And my advice is just to you spend 2 hours on this and 2 more hours on this. Just to, if you are comfortable and if you are able to recollect whatever you have already studied previously, it is okay. Otherwise, if you feel 2 hours you are not getting, even if you spend another 3-4 hours on it, it is worth it. Because without doing it, exercise, if you directly start going and trying to learn something in quantum computing, it is of waste. But once if you are comfortable, very much comfortable with these two, and you need not know the whole about complex numbers and vectors, the basics I'm telling. So in complex numbers means what are the three representations of the complex numbers? That is rectangular representation, then what is that, polar representation, and exponential notation representation, and how to like convert from one form to another form. So that part you need to understand. And in vectors, you need to know what is vector and what are the possible operations that you can do on vectors. So vector addition, subtraction, multiplication, division. So when you go with multiplication, we have three kinds of multiplications: dot product, then cross product, and a tensor product. Just if you understand these two, I'm telling you, you will enjoy the whole subject like anything. Okay, all the algorithms, whatever now I may be showing you 6 algorithms that we discussed in the class. Of course, one I already told, which is nothing but that Shor's algorithm, and a few more algorithms just we'll see. But to understand all those algorithms, you must be aware of these two with at least comfortness in this whatever the words that I told. Okay, all the operations on vectors and converting one form to another form of these complex numbers. Okay, great. Now, I think have you come across this sphere, which is known as Bloch sphere in quantum? Okay, actually this is used to represent the qubit. During the last summer, almost we spent 7 days to understand it perfectly, but still I can't say I understood it perfectly, but at least I can say it is 80% understood it perfectly. But okay, as we are having some inbuilt functions in Python, after understanding 80%, we feel like okay, remaining part is going to be okay, kind of thing. Okay. Anyhow, so you understand this is nothing but representation of the qubit from initial state to some of the state of the qubit after doing some processing. What do you mean by doing something on qubit? I think in classical, what do you mean by something doing on a bit? We use gates. Okay, in quantum, instead of bit we have qubit, then obviously we'll have quantum gates. Same thing. Then in our whole classical computer, the gates are used to make circuit. Here, same thing.
జనార్దన్ పేరు
Quantum circuit.
జనార్దన్ అతను
Just we are using the word quantum before whatever that we studied classical. Bit, quantum bit, gate, quantum gate, circuit, quantum circuit. So writing a program in quantum computing as of now is considered as designing the circuit. Okay, so as you given now, so as this is the gate, and so we'll see. I think have you come across different quantum gates? Can you tell if you come across the names of some gates?
Not C naught.
Okay, very good. Then you are very good here. It's easy to remember. Then let us assume that if you have one gate yes, then what is your corresponding gate for S? Just for fun, I'm asking. CS. Is there? This gate also there? Okay, now just because just by saying, because you told these two things continuously, that's why I'm telling that immediately I got that idea. Okay, now very nice, good, good. So not and C not. Yeah, any other gates?
One
Okay,
more,
those are the. Yeah, sorry. Huh?
one more gate there, sir. I forgot.
Okay, okay. I'll show you here. Yeah, see, actually, these many gates at least we explored. Out of this, we are able. I can say that except 2, 3, we explored everything. So anyhow, identity gate there is no poly X gate. That is what you told. No, not very good. And your C naught is here. In addition to that, we have Y gate, Z gate, then Hadamard gate, phase, then phase T, then rotation, 3X gates, 3 rotational gates, then control not. No, so you can extend that control to n number. Here it is CC naught. Then if you write C4 3 Cs, then triple C naught. Then you can say 4 Cs naught. Otherwise, you can write it C4 4N. So like that, you can extend that control to n number of control bits. Okay, that and all will be saying at least. Okay, at least you understood that gates are there. Okay, so that is very very important. Then only you can understand in the whole. As I think here I have written now here. So writing a program is nothing but making a circuit. So how you can make a circuit? By using quantum gates. So that's why we must go through all the gates to understand it. So that's why I'm telling you once again, please you go through a, a particular syllabus and try to learn in a systematic way. Then you will enjoy this whole subject. Otherwise, simply taking one article and reading that, it won't serve our purpose. Seriously, I'm telling it. Okay, you may get the feeling of saying that okay, you are studied, but if you somebody asks you to do something in that or extend it, it is very impossible to do that. Okay, right. Now just I'll tell about image processing and directly I'll tell you what is quantum image processing. Okay, because see, only two things I want to tell here is so quantum computing. Please, whether you are listening everything or not, it doesn't matter. But please, you try to understand it. Only the one which I'm writing now. So quantum computing, you need to know about complex numbers and vectors. The whole quantum computing, theoretically, I'm telling, it is all about doing something on these two concepts. And the whole image processing is nothing but array processing. So if you really keep this in mind, and if you start learning anything, actually you will be telling that you there is nothing in whole image processing and whole quantum computing because I'm in image processing from past so many years, as I told, more than 20 years. I didn't find anything other than array processing, normal array processing. Okay, I'll tell you what is that. That means even a 10th class student who knows programming and who knows for loops and if condition, he also can start working with the array processing. In the same way, here a 10th class student who knows about complex numbers and vectors, he also can understand quantum computing. And it's theoretically the superposition is somehow we need to convince him, or we also, because in the beginning, even I also a lot of confusion to understand the meaning of superposition, but it's now a little bit convinced myself. Okay, there is some concept known as superposition. If you really keep this in mind and you start reading anything, then you will enjoy. After that, whatever the words, whatever the technology that they use, no, it is all about only these three concepts. Yeah. Now, image processing, you see here, this is considered binary image, gray level image, and color image. When you open that first photograph, you are going to see it like this. Let us assume this is your that image. If you open that by using any of the image processing supporting software, you are going to see it like this. Now, let us assume that you don't know this part now. So all of you understood this one now. I assume that all of you know some good. You're good in programming. I have given you one array A, and asked to get an array B, such that replace 1 with 0 and 0 with 1. Can you write code for that? And you tell me how many approximately how many lines of code it is required? Approximately. Making a B from A. That means I need to get the result like this. Can you tell me approximately how many lines? Is it 6,000 lines?
Like it may require 4 lines.
Yeah, approximately it is 10 lines. That's all. But it is not a big task. No, now you tell me, a first year BTech student can write a program for this after completing C programming. At least assume that he is okay, is comfortable with for loops and if condition, and he knows what is array. I asked him to write a program for this. It's very much comfortable now, BTech first year. And assume that otherwise, I heard that in central schools, ICSE or CBSE, the students may be studying programming in 9th or 10th standard itself. Then they also can write a program for this now. Then why we need to have BTech, MTech, PhD for doing image processing? Not at all required. This is sufficient. More than your 10th class knowledge of programming is sufficient, because somebody is giving us array and we got one more array. That's all. Then after this, okay, we may not be knowing how to display the photograph. Now, can you tell me how the output is going to look like after doing this process for this photograph? Okay, this is the original photo. You got ones and zeros. I asked to modify that ones and zeros with 0, 1, this one, and you are displaying the photo. Now, that means I have given you one photo.
Like black color changes to white color changes to black.
That's all. That means have you processed this photograph or not?
Yes, sir. The colors will change. Like
Yeah.
black color, in place of black will come white. In place of white will come black.
Yeah. So that means you processed this photograph. I can say you processed this image, or I can say that you processed this picture. So these are the synonyms of this word photo. That is nothing but your image processing but as you are doing with the computer, that's why we call it as digital image processing. So by chance, instead of this, if I have given you this as one printout and ask you to convert black to white and white to black, whether you were able to do it or not. Otherwise, you assume that I have given it to a small kid, a second class student, and ask him to make black to white and white to black. Can he do it by himself or not? No image processing, no computer, manually. I have given the hard copy to him. Obviously, he will take two sketch pens, black sketch and white sketch. Wherever there is white, he will start using that black, and wherever there is black, he will be start applying white, and slowly he will be showing that yes, he processes that photograph. Now, same thing, whatever that human was doing, now we are taking the help of the computer to complete it. But what is that you have done as a programmer, the great programmer, if you feel? Nothing. You have just replaced 0 with 1, 0 and 0 with 1. Then by that we are claiming that we did digital image processing. That's all. Okay, because that is very simple task, it's okay. Now let us assume that you go with the other image, second photograph. You tell me what is the difference between these two photographs, first photograph and this second photograph? Okay, here also it is a photo, but instead of having that only two shades of black and white, now you are having some n number of shades. But n number of shades is all depends on how many number of bits that we use to represent a pixel. And for your information, I am telling the pixel is made by using the two words picture element. By using these two words, pic and el, they made the word pixel. Because inside the computer, each one is known as the element of the picture. And we know that each pixel is nothing but one number. And at the same time, we know that to store some numbers inside the computer, we need memory. And if you go back, we know that memory is going to be measured in bits or bytes. Okay, now somebody is saying that their computer is supporting 4 bits to represent a number. And as I told, number is nothing but pixel. Now I'm writing it like this, 4 bits per pixel. Then what is the minimum number and maximum number, decimal number that you can write by using 4 bits?
Like 0 to 15.
Yeah, very good, 0 to 15. And 0 is always used to represent the darkest pixel.
Black color. Yes.
Yeah, black color, and 15 is for the brightest. And somebody said that their computer, his computer is supporting 8 bits per pixel. Then what could be the minimum and maximum? What is the minimum and maximum? Minimum is 0,
0 and 255.
255. But somebody said it is 10 bits. Then minimum is 0, maximum is 1023. And generally, most of the people they maybe have the feeling like a gray level image means 0 to 255. This is the correct answer, but this is one of the correct answer. Don't feel that this is the only correct answer, because previously in the beginning era of this image processing, they used to have only 4 bits per pixel in particular software at that time. So 0 to 15 is correct answer. Now, even there are some medical image processing supporting softwares. They use 10 bits per pixel to represent this black and white photo only. So obviously more number of bits per pixel means more clarity. Obviously that will use more memory also. Okay, anyhow. So once it has this gray level image, if I open this by using any of the image processing supporting software, here also I am seeing numbers. Then what is the difference between your previous numbers and these numbers here?
Like a range of numbers.
Yeah, previously you have only 2 distinct numbers, 0 or 1. But here you are having some range of numbers. And as it is considered as gray level image, we know that 0 is used to represent the black, darkest, and 255. I'm assuming 8 bits per pixel, and 255 is considered as brightest. Now, if you assume that your computer is supporting 8 bits per pixel, then can you tell me what are the possible values in this array? First row. They are nearer to 0 or nearer to 255?
Near to 0.
Nearer to 0, very good. What about the values over here? Nearer to 0 or nearer to 255? This white part.
255.
255. What about the values over here? They're in between, no?
Like 100 to 200.
Yeah. Okay, we'll take the average. Whatever that you told, no, I'll be taking the average. Okay, right. So they are the numbers like this. And if you observe it, no, I'm using the word nearer. Nearer to some number. Because I can't say just whether it is 0 or 1 by seeing with my eyes. Because our human eye can't distinguish the gray shades which are very close. If I keep 2 shades with number 0, 1, 2, 0, 0, 1, 1, if you ask me to tell, okay, these are the numbers. But if you display the photograph by using these 3 numbers, nobody in the world can recognize the difference among these 3 numbers with their eyes. But when it is for computer will identify or separate 0 as 1, 0 as 0, 1 as 1. Okay. Now, you tell me now, I am asking to write a program to replace her black hair with white hair. This is array A. Can you tell me what is the processing now for this array?
Like replace 0 with 255.
That's all. Then how many lines of code that you require for this one? Approximately. Same 10 lines, no?
Yes, sir.
Yeah. Then after that, now if I ask you to display, if I tell you how to display this photograph, then you will be displaying the processed photo. That means now by doing it so, you can say that you know how to process binary photograph, you know how to process gray level photograph. Okay. Now you tell me, this is a very important point. After observing both these examples, is there anything other than array processing?
No, sir. It is only ND array processing.
Yeah. So that is what you keep in your mind throughout your life. If at all, if you want to explore image processing, how big the algorithm may be, how complicated it may be, for a programmer, it is nothing but array processing. People let them start talking about medical image processing, then finding the cancer is there or not, or some other radiology, radio image, or X-ray image, or like what is that? Sound image. What is it? Ultrasound image. For that, this. Once if you keep any photograph inside the computer, it is treated as an array. And doing something to these numbers and getting one more array and displaying it is all about array processing. Okay, it's the array processing. But now onwards, you can call it as image processing. That's all. Really, I didn't find anything other than array processing in the whole image processing domain from past 23 years. So that's why it is very, very, very easy topic to explore. Those who feel like they are very comfortable. But once if you start studying it, you might be getting some algorithm, which may be, people say very difficult. But how much difficult it may be, they are telling what to do for these numbers in this array. And you give me the modified values, write it here in one more array, then display it. Even if you say that you have written a program to detect the cancer in the photograph, cancer in the photograph is nothing but an array to us, as long as we are from image processing part. That's all. If you keep that in mind, then no, you need not really go through and go to anyone to ask about it. So it is up to you to take one algorithm and start studying it and understanding it. If at all, if you say you are not understanding, it is the problem of your maths, which may be a little bit more explained here, or you are not spending time. But if you spend time and if you are comfortable with the terminology, everything that they talk is all about doing something to the given array and get one more array. But instead of saying one more array, then small example, then we can go to quantum part of it. So this is an image. Now let us assume that I have given you this photograph and ask you to count the number of people in this. What is your answer? What is the number of people in this photograph? Two. Yeah. So that means, have you processed it with your eyes or not? First, you have you are seeing it with your eyes, and whatever that you have seen is you send to your brain. Brain knows how to say this is human being, this is human being, this is not, this is not, this is not, and brain knows how to add all the numbers. That means you process this photograph. Is it right or not? But output is what now? Output is an output is another photo here. No, output is not another photo. Output is some statistics. So from now onwards, you remember that image processing, the input is image, output always need not be an image. Output can be some statistics of that image. Okay. Now see, once if you go like into this image processing, there are a number of things to be done, like image enhancement, image compression, morphology, segmentation, then what is it, filtering, then removing the like noise removal, almost all chapters which are there in our prescribed Gonzalez textbook you can explore. But now all those things can be done in the quantum environment. That is the main intention here, to show that. I'll show you that paper, then you will get confidence about this. Yeah, lessons from 20 years of quantum image processing. Okay, so people started doing around 20, and this paper, if you see, it is taken just exactly 1 year back. Okay, then if you go through this, at least here, you can see these are all the things that they have done in quantum environment. But did it for images, segmentation, morphology, then pseudo color processing, encryption, steganography, watermarking. And if you even go back, actually edge detection, filtering, matching, I don't know what is matching, and classification, comparison, rotation, translation, compression, interpolation. All these are the actual contents of our image processing. But now all those things, they proved that you can do it in quantum environment. Now how to do it? By using that same diagram which I have shown in the beginning. What is the diagram? Okay, by using this diagram we need to do. Okay, convert the classical into quantum, do this, and finally you will get it. Okay, now one simple task I'll show you what we have done by using this. So I'll be showing you like image negative part, which we have done by using quantum environment. A simple example to understand. After that, so one of my PhD scholar and MTech student, they will be showing the code also in this. So we have time up to 4:30 now. What is the time? organizers?
Sir, till 4:15, sir.
4:15. Okay, okay. Yeah, 1 second. Then give me just a moment time. Call Amit.
Calling Amit.
Yeah. So is it visible screen?
Yes, sir, visible, sir.
So actually this is known as the like our photograph and small array. So this is actually, this is the given photo and this is the corresponding negative. This is also known as one of the image processing tasks. But as I told, this is nothing but array. I am taking some small example. That is 0, 5, 10, 15. Okay. So okay, sorry. Yeah, now can you tell me how to get the negative of this one? I think most of you might have seen the negative of the photo. Can you guess what could be the like mechanism or algorithm for this? It is only one line algorithm.
I could 255 minus that matrix.
Yeah. Okay. If it is 255, if I say 8 bits, so it's okay. But now let us assume I'm telling only 4 bits per pixel. That means obviously you need to subtract everything from 15. So 15, 10, 5, 0. Okay, see the whole image processing, if at all, if you want to start doing, no, don't directly do it on the actual image. First, you do it on array, write a program. So instead of when you write a loop, no, instead of saying I equal to less than equal to 2, better you write I less than equal to m or n, whatever, n1 and n2. Then once it is perfect, then simply you are replacing this with this array because it is nothing but an array. So now I'll be showing you how this image negative has done in quantum environment. Okay. So first we need to represent the given image in one of the image representation, that is NEQR. So this is considered NEQR representation. Here we have to okay, and this is known as direct notation of that circuit. So here it is going to show the location and gray level value. And here how many qubits we need to take is depending on what is the number of positions and number of gray level values. As the number of positions are 4, 0, 1, 2, 3, 4. So 2 qubits are taken to represent the position, and 0 to 15, that is 4 bits. Okay, we used 4 qubits to represent the gray level value. Okay. Now, as our target is to first keep those numbers in the circuit, so we use NOT gate. And can you tell me what is this gate? Those who have studied about gates, this blue color, CC NOT. And this is NOT gate. And what about this one? H stands for what? Which gate? Hadamard gate. Okay. So by using those two gates, actually we made the circuit. So by doing the circuit like this, we can guarantee that these numbers are there in the circuit. Sorry, I think I'm not able, because of the time limit, I'm not explaining it in detail, but at least you observe that if you start, because and this is the very easy representation. That's why I've taken NEQR representation. Otherwise, if you go with FRQ and other representation, it is very difficult to understand directly. But that may be efficient or very less qubits may be used. but easy to understand is this. If you understand only our normal bits, easily you can understand this. So simply changing 1 to 0 and 0 to 1. By doing it like this, I can say that the input is there in the circuit. Then after that, as our target is to change 10 to 0 as 15 and 5 as 10 and 10 as 5 and 15 as 5. So simply I'm changing these values here by applying the NOT gate. So I think all of you know what is the meaning of NOT gate. Just flipping the bit. If it is 1, it is making 0, 0 as 1. Previously, as I have all zeros here, I'm making 1. That means 15 is here. Previously, what is 0, 1, 0, 1? The black color. 0, 1, 0, 1 is 10. So I made that 10 as 5, 1, 0, 1, 0. Then what is this black representation? 1, 0, 1, 0. So 1, 0, 1, 0 is made as 0, 1, 0, that is 5. And all ones is made as 0. Then we have done the same thing in IBM environment, designed the same circuit and executed there and written the code for this whole process. And we were able to get the correct result of converting, getting the negative of the photograph. And once it is done on one image, doing it on all other images are going to be very easy. And we did it on even the color images. So doing it on color image is nothing but doing the same program for 3 times. One on red channel, green channel, and blue channel. So that is what we have done so far. Now my student will explain about noise detection or noise removal. Because I have shown you in the previous paper, you can do anything which is actually the part of your basic image processing. So one of my PhD student, she is doing her PhD in noise removal in quantum domain. So now she is going to explain that with some in 10-15 minutes. And 10 minutes she will explain, or 7 minutes. In next 7 minutes, my student will show the code which is related to this quantum execution part. Yeah, please, Shanti. Can you come here? Is the screen visible?
Yes, sir.
Good afternoon, everyone. Myself Shanti. I'm doing full-time PhD under the guidance of. Myself Shanti. I'm pursuing full-time PhD under the guidance of Vivek Raju sir. Am I audible? Can you respond, anyone? Am I audible?
Yes, ma'am.
Yes, ma'am.
Yeah, thank you.
You tell it loudly, Shanti.
Okay.
More loudly.
Yeah, here we are discussing about the something related to the image processing. So here I'm explaining about the what is noise in the image. So here the not only the term noise refers to in the image. So we can use anywhere in the term noise refers to. Dictionary meaning is unwanted or unpleasant. So here we are discussing about the images, right? So I will tell a small example. Suppose here I'm listening music. So due to the weak signals, I'm getting some unwanted disturbance. So this is called also one type of noise in the music system. So here we are talking about the images, right? So here also the image consists of set of pixel values, intensities values. So here the term noise refers to in the image means unwanted pixel values that are not part of the original image. So here we can clearly see that how the noise images will be. So here these are the not original images. These are the noise images. It means some unwanted pixel intensities values are added to the original images. So this is called noise in the images. So how the noise enter into the image means there are some causes to enter into the image. So these are the causes of noise, sensor limitations and transmission errors, compression artifacts, low light environments, and faulty memory storage. So I'll give one or two examples for the causes. Suppose I'm capturing the photo from the sunlight condition. So here the image will get that much clarity? No, right? So the image may not contain that much clarity in the sunlight. So this is also one type of causes of the noise, that is called sensor limitation and transmission errors. So these are the causes of the noise. So there are different types of noise available in the real world or image processing. So Gaussian noise, salt and pepper, uniform and relay, along exponential and periodic noise. So here we are going to concentrate about only on the salt and pepper noise. Salt and pepper noise. So these are the various types of noises available in the digital images. So we can see every image, consider the Gaussian noise, that images have some graininess appearance, right? So this is not the original image. This is Gaussian noise image. So for every noise, we have some traditional methods, deep learning or quantum methods are also available. So here we are focusing on only salt and pepper noise removal. So consider, so while coming to the salt and pepper noise in the image, so the image consists of some white and dark pixels scattered throughout the image, right? This salt and pepper noise image. So to remove these types of noise, we can use median filter in the traditional methods. So or else we can use deep learning methods, quantum methods also available to remove this type of noise. These are the another possible noise available in the digital image processing. So these are the noise removal techniques which we use it to remove salt and pepper noise. So the first thing is traditional methods. In traditional methods, there are two types of domains, spatial domain and frequency domain. So there are different types of filters are available in the spatial domain as well as frequency domain. So these are the deep learning methods, UNet, autoencoders. Other than this, we can use transformers, attention mechanisms also use it to remove the salt and pepper noise. So here we are discussing about only one of the quantum method, which we use it to remove the salt and pepper noise. So here I'm taking the small example of the 4x4 matrix. So here I'm taking one small 4x4 example, how to detect noise. So here it is the image consists of 3214 4x4 image it is actually. So how to okay. So this image consists of 4x4 matrix. So suppose we'll assume this is the image. So here it consists of some values. So first we need to identify that whether that image having the salt and pepper or noise. So how to detect noise? So here in this research paper, they give one mechanisms to identify the salt and pepper noise in the image. So here it is the noise detection mechanism. See here, it is the formula. So whenever we are considering a window of the 3x3 window. So in that window, minimum value and the maximum value. So these both are considering as a noisy pixels, and the remaining signals are noise-free pixels. So here the noise removal method is, so wherever we are finding the minimum value or maximum value, we need to consider it as noisy pixels. So to remove these noisy pixels are replaced with the median value. So here we'll take one small example and we'll solve this example. So here it is considering salt noise. So in the 3x3 window, so wherever we are finding the maximum value in the 3x3 window, that is called salt noise. So consider this 3x3 window. So can you tell anyone, is there any, what is the salt noise of this 3x3 window? 3 to 1, 5 to 6, 7.
7.
Yeah, yes, please. Can you come again? Yeah, 7 is the maximum, right? So here it is considered as the salt noise. And pepper noise means minimum intensity value. So here it is the 0. 0 is the minimum intensity value. So here it is considered as pepper noise. So within the 3x3 window, wherever we are finding the minimum value and the maximum value, we are considering it as noisy pixels. So our method is median filter. Wherever we are finding the median filter, we need to replace with that median.
Yeah, please can you tell me how many are pixels here now? Please, all of you try to understand. Just 1 second. Very good. Just I'll add one statement here. See, as this is the given array, so our task is to find out the noisy pixels. But according to this explanation, we said that we can go for some padding. Because image processing, one of the technique is considered as padding. So just to process all the elements, why this and all will, as next time we'll see in detail. Padding 7 means just I am adding one row and one column in all the directions. Now we need to decide whether 3 is noisy pixel or not. It means you need to consider all its 8 neighbors, including that. Is that value that you considered is minimum or maximum among all the elements? Is 3 is the minimum or maximum among all the 9 elements in this case?
No, sir.
No, sir.
No, that means that is not a noisy pixel. Okay, then so this is the correct, not noisy. What about 2? Is it minimum among all the 9 neighbors of it, including that 8 neighbors plus 1?
Yes,
Is
sir.
it minimum? No,
No.
2.
What is the-
2, sir.
Not, 1 is there, no, that's why it is not a noisy. What about 1? Is it the minimum among all the 9 elements?
Yes, sir.
Yeah, so that means this is noisy pixel. What about 4? Not
No,
noisy.
sir.
5? Not noisy.
No, sir.
I'm putting tick mark means it is not noisy. When I write n, that means it is noisy. What about 2?
No, sir.
Okay, 6?
No, sir.
No. It has to be either minimum or maximum among all the 9 elements.
Yes, sir. It is maximum of
Sir,
that 3x3 matrix.
Yeah, because in 3x3 this is noisy only, no? You are considering
Sir,
6.
if we consider 7s,
Where no, you are considering 6. Why? Because this is the center, no? Why you need to consider 7? Taking that as the center and consider it 9 values.
okay,
You
sir.
can't-
It is.
If you by chance there is something known as 5 by filtering, then 7 by 7, then you will be considering extra rows and columns. But here we are considering 3 by 3. That means you are at some place, you need to consider it 9 neighbors. Then next time when you move to some place, then you need to consider it 9 neighbors. When you go to some other location, next location you need to consider its 9 neighbors. Okay. What about 3? Not noisy. 7? Noisy. Because you need to check.
It equals with noise, sir. It equals with 7.
Yeah, the one you considered, it has, if you consider either maximum or minimum, then that is considered as noisy. Okay, then this is noisy. 6 is not noisy. 0?
Noise.
Yeah, noisy. That's all. So we'll be getting, and 2 is noisy. We did it already. So now we need to replace only these 5 noisy pixels with the respect to median. That's all. That is the algorithm. You got it?
Then is there any rule for applying padding? Like how many rows of padding? Like what number to add the pad?
Yeah. It depends on how much neighborhood that you consider. because I considered 3 by 3 neighborhood. That means if I whatever the pixel I considered, I should have 9 values because 3 by 3 means 9, no? Then to get 9 values, I padded with one row. By chance, if somebody says that I need to go with 5 by 5 mechanism, 5 by 5 structuring element, then that means when I go to some location, I should have it's 25 neighbors. Then, but to get this 25 neighbors to this 3, I need to add one more row here, no, and one more
Yes, sir. Yes,
column.
sir.
So that is how we generally do in image processing. So
Like
that is
about
the-
number, like which number to pad, like is it a random number or can you use any maximum number, minimum number?
No, there is no such rule. There are actually in image processing we discuss so many methods. The padding it is up to the user. So some people say padding with 0, then padding with some
Yes, sir.
random.
Like in deep learning, we will use deep zero padding, sir. Like
Yeah,
just for extra rules.
that's all. Only to get extra, but nobody knows. Nobody why you are written 0. Okay, just everybody is
Like we like in deep learning, we will try to consider the maximum feature. Like the maximum feature will be like maximum number.
Yeah,
So it will be high intensity value.
yes. So, but okay, there you consider like 0 to 50 it's up to according to the what is that algorithm that you are using. Here also same thing, but instead of that, sometimes the people use a replication. That means same row will be copy pasted there. That is also one kind of padding. And recently, one of our MTech student told, what is that padding? Wrap around padding. Just you can explore it. Okay, right. Now she will continue. Sorry, I think we don't have time. Right. Now give us 5 minutes time. Is it okay, organizers? Organizers, is it okay? 5 minutes, last 5 minutes. Hello?
Sir, please proceed, sir.
Okay, right.
Please proceed, sir.
Thank you. Yeah.
Okay, so this is the quantum method representation. These are the steps for quantum Gaussian filtering. The first step is we need to convert the classical image to quantum image. So it means we are following here NEQR representation. So it means input ready. So we are taking input ready. We are converting classical image to quantum image. So then we are adding some ancillary qubits. So here what is the need of ancillary qubits means we are processing something so that to store temporary values we use ancillary qubits. So here in the 3 by 3 image, so total 9 intensity values are there, right? So to store the each value in the binary form, suppose we are considering 0 to 7 values in the 3 by 3 image, 0 to 7. So total 9 pixels are there. So each pixel having the binary value 3 bit, right? So we need to have total 9 into 3, 27 ancillary qubits to store the values in temporarily. So this is the second step of the method. So the third one is cycle shift transformation. And the fourth one is calculation of min max median. So here after calculation of min max median, we'll detect the noise, whether the noise pixels are there in the image. So then we'll replace with the median. So these are the indicator representation of the image. So here it represents the grayscale value of the image. So here it represents the qubit. So how many qubits need to represent the position values? Okay, so this is the unique representation of the image. So next, my friend Amit will continue with the practical example of the unique representation.
Yeah, you need to close it in 2 minutes, 2, 3 minutes.
Okay.
Sorry for that.
Yes. So this is I'm Amit. I'm explaining the implementation part. So just I implemented all this concept noise removal into Jupyter. So this is a representation of the 3 by 3 matrix. So here we took at the start 3 by 3 matrix, right? Okay. Here it is not there. Okay. So to represent like okay. So So here, suppose if you want to show these things, so this is what positions. These are, we required 3 positions to represent intensities of the each pixel. So why 3? Because in matrix I have considered only 0 to 7 values. So for 7 values, only 3 intensity required, right? That is for 7 it is 3 bit, only 3 bits required. So that's why I taken 3 grayscale values. So 1, 2, and 3, and this is the positions because I consider 4 by 4 matrix. So for to represent 4 by 4 matrix, we require 4 positions because 15th position 0 to 15. So to represent 15, like 1, 1, 1, 1. So 4 bits required. So that's why 4 positions. Now first value. So may I know what is this values? Can anyone tell me this value? The first one. So here, so the first value here is G0 is 0, G1 is 0, and G2 is 1. So first value is 4. So initially all are zeros. Initially this circuit is empty. So 0, 0, 0. Then if you want 1, 0, 0. So first we will apply a NOT gate on all positions to get 1, 1, 1. First, this is the first step. Then to represent, then we will add CC NOT gate to get 1, 0, 0. So similarly for all other values. So this is the second step to add ancillary qubits, as sir and ma'am discussed in the paper. So we have to add this ancillary qubit because we have to store 9 pixels. So for each pixel, 3 values. So 27 ancillary qubits. So here is a one cyclic shift operation. How we can do, like also like we are to get all neighborhoods of this 5. So we need to bring all neighborhood into the center of this 5. So first we'll get 2, 3, 6, 9 like that, and then this is a representation of neighborhood pixels in
Yeah, Professor Raju, thank you very much. Hope I am audible to you all.
Yes, sir. Audible, sir.
Kiran, please provide vote of thanks, Kiran. Thank you very much, Rajgaru. You have taken exhaustively. You gave some examples also.
Yes, sir.
By showing. It helps a lot. As I mentioned, the same thing is kept in our YouTube channel. It helps several people to understand, to go through easily. Thank you very much. Kiran, may please continue.
Sir, thank you, sir, Raju, sir, for providing us the theoretical and also the practical exposure on the image processing applications with respect to the quantum computing, and same with respect to the difference between the traditional and the quantum aspects also, sir. And thank you, sir, for sharing your experience and expertise in quantum science and technology, and showing the pathway to move towards research aspects in the image processing area also, sir. And on behalf of Center of Excellence on Quantum Science and Technology and JNTU Kakinada, I express our sincere gratitude towards to our distinguished speaker, Professor Yosan Raj Garu, for delivering such an insightful and enlightening lecture. Sir, your valuable suggestions, expertise have greatly enriched our understanding and inspired all of us to move towards in this area, sir. And thank you all the participants who made this program a successful one. And we are organizing a couple of sessions with respect to the quantum science and technology on behalf of Center of Excellence on Quantum Science and Technology, JNTU Kakinada. And next week we'll be meeting again with the same Zoom meeting with some other expert delivering their experience. Thank you one and all. Thank you, sir.
Thank you, madam. Thank you.
Dear participants, we'll meet soon next week. Thank you.